Hi guys, and welcome to a new video on this series about data mining the social media. And today we're going to talk about mining your followers. So in the real world, the social community is a group of people who share some common conditions. This broad definition includes, for example, communities of people located in a precise geographical area, people with the same political or religious belief, or people sharing a specific interest, such as reading books. The concept of social communities is also central to social media platforms. The boundaries of a community in a virtual environment can be more blurred than in the real world, as, for example, the geographical aspect is less determined. Just like in a face-to-face situation, a community naturally appears on a social media platform when people with common interest or conditions start to interact. We can make the first distinction between different types of communities depending on whether their members explicitly understand being part of it. In explicit communities, members and non-members know exactly whether they belong to the community or not, and usually understand who the other community members are. Interactions between members of the community are more frequent than with non-members. On the other hand, implicit communities come into existence without being explicitly acknowledged. Members of this type of community might share common interests without having clear and strong connections. So in this section, we will propose to analyze user data in order to segment a bunch of user profiles into groups with the purpose of highlighting what these common interests or conditions are. Clustering or cluster analysis is a machine learning technique used to group items in such a way that objects within the same group, that is cluster, are more similar to each other than to objects in other clusters. Clustering belongs to the category of unsupervised learning techniques, meaning that the objects we are dealing with are not explicitly labeled. The purpose of unsupervised learning is to discover hidden structures in data. A common example of an application of clustering is market research. For example, to segment a population of customers with similar behaviors or interests so that they can be targeted with different products or marketing campaigns. Social network analysis is another important field where clustering finds interesting applications, as it can be used to recognize the structure of a community within a larger group of people. Clustering is not just a specific algorithm, but rather a general task that can be approached by different algorithms. The one that we choose for our analysis is k-means, one of the most popular approaches for clustering. K-means is a convenient choice as it's relatively simple to understand and implement, as well as computationally efficient when compared to other clustering approaches. K-means takes essentially two arguments, a number of input vectors in n-dimensional space, which represent the objects we want to cluster, and k as the number of clusters we want to partition our inputs into. As we are in an unsupervised learning setting, we do not have any ground truth information regarding the correct category labels. To be more specific, we don't even know the correct or ideal number of clusters. This detail is quite central in cluster analysis, but for the time being, we won't worry too much about it. So as I just mentioned, the objects that we want to cluster as vectors in the n-dimensional space. In simpler words, this means that each user profile is going to be represented as a vector for n numerical elements called features. The approach we choose to define these features is based on the user's description, that is the textual information they provide about their interests or occupation. The process of transforming this textual description into a vector of features is called vectorization. Both the k-means algorithm and the tools for vectorization are implemented with a straightforward interface in scikit-learn, the machine learning toolkit for Python, which we all encountered in the first series, Social Media, Social Data in Python. The vectorization process involves breaking down the user description into tokens and then assigning a particular weight to each token. The weighing scheme adopted in this example is the common TF-IDF approach. If you check this link, you can get the details. And TF-IDF is it's the combination of term frequency, which is TF, and inverse document frequency, which is IDF. And TF is a local statistic, as it represents how often a word appears in a document. On the other hand, IDF is a global statistic. It represents how rare a word is across a collection of documents. These statistics, commonly used in search engines and different text mining applications, provide a measure of how important a word is in a given context. TF-IDF provides a numerical weight behind a simple intuition. If a word is frequent in a document and rare across the collection, it is probably very representative of this particular document, so it deserves a higher weight. In this application, we are basically treating user descriptions as documents, and we use TF-IDF statistics to represent these under descriptions as vectors. Once we have the n-dimensional vector representation, the k-means algorithm can use it to calculate the similarity between them. So I've written a script here, and it takes advantage of the facilities offered by the scikit-learn, in particular the TF-IDF vectorizer and k-means class. So I'll pause it. Please pause the video and copy the code, and I'll scroll down in a second. So as TF-IDF vectorizer has a number of options to configure the way the vectors are calculated, we will use the argument parser part of the Python standard library to capture these options from the command line. The getParser function defines the arguments as follows. File name. This is the path to the JSON-L file that we want to analyze. --k, this is the number of clusters that we want. And min_df, this is the minimum document frequency for a feature. The default is 2. Max_df, this is the maximum document frequency for a feature. The default is 0.8. Max features, this is the maximum number of features. The default is none. No IDF, this flags whether we want to switch the IDF weight off using only the TF. IDF is used by default. And min grams, this is the lower boundary for n grams to be extracted. The default is 1. And then we have the max n gram. This is the upper boundary for n grams to be extracted. The default is 1. So let's run the script. I've already done it. Where I take the file that is stored. Followers, the JSON-L file, 5 clusters, max features 200 and max n-gram 3. So let's run it. So I'll just come back to this in a second. So we can limit the number of features being extracted by the TF-IDF vectorizer, either explicitly using the max features or specifying the desired range for the document frequency of a feature with min df and max df. The minimum document frequency is set to 2 by default, meaning that features that appear in less than 2 documents will be ignored. On the other hand, the maximum document frequency for a feature is 0.8, meaning that features appearing in more than 80% of the documents will be ignored. Depending on the size of our dataset, we can decide to be more or less conservative with these values. The purpose of excluding features based on their document frequency is to avoid calculations for features that are not representative of the task. Moreover, limiting the total number of features with max features is also meant to speed up the computing, as the input is smaller. When this option is specified, the most frequent features, depending on their document frequency, are chosen. Different from the other arguments, the no IDF option is not used to specify a particular value, but rather to switch off the use of IDF, meaning that only TF would be considered when computing the feature weights. The argument parser allows us to specify how this argument behaves by providing a variable name as the destination. Dest is equal to use underscore IDF, and the action to perform when the argument is given is store false here, while the variable defaults to true if the argument is not provided. IDF is normally used to scale down the weight of terms that are very common across a collection of documents, and hence don't have any particular discriminative power. While in many applications it makes perfect sense to adopt IDF in your weighing function during the exploratory data analysis steps, it's still important to observe its effect, and hence the option to switch it off is simply an extra tool in our box. The last two arguments allow us to go beyond individual words and use n-grams as features. Generally speaking, an n-gram is a contiguous sequence of n items. In our application, we have a piece of text that is tokenized into a sequence of words. Individual words are also called unigrams. N-grams with n equal 1. The other commonly used n-grams are bigrams, which is n equal to 2, and trigrams, which is n equal to 3, while larger sizes can be used depending on the application. For example, given the sentence, "The quick brown fox jumped over the lazy dog," its bigrams are defined as the quick brown fox, fox jumped, and so on. The benefit of using n-grams rather than just unigrams is the possibility of capturing phrases. So if you look at these last two sentences, these are fictitious sentences. For example, he's a scientist, but he doesn't like data, and he works as a data scientist. But only using unigrams, the terms data and scientists would be captured in both lines, even though they are used in different ways. While with bigrams, we can capture the phrase data scientist, which provides a different meaning compared to the two words individually. By default, the lower and upper boundaries for n-grams are set to 1, meaning that we are using only unigrams, if not specified differently. So to conclude this description of how the TF-IDF vectorizer is configured, we will notice that it also used the stop words argument defined to capture stop words from the English vocabulary. This is a list of common English words such as the and, which do not carry particular meaning per se and are probably used in almost every piece of text. While in common English, stop words would probably already be filtered out by the max DF option, as their document frequency would be close to 100%. Users on Twitter often don't use fluent regular English, but just a list of keywords representing their interests to overcome the limitations with numbers of characters, the 140 character limit. TF-IDF vectorizer also allows the stop words attribute to take a custom list of words in case we want to personalize it. So running the code as we did, I have the following output. So we can see the first one, if I'm to analyze this, is mostly about purposeful living stuff. Yeah, it's more profound stuff and more like wisdom type of statements. Not here, maybe. Yeah, it's more of a motivational stuff. And cluster 2 is mostly about travel, it seems. Some Norwegian here. Also some telecom stuff. So, and cluster 3 is mostly about web. It seems web development. Web. It's mostly about web. And cluster 4 is Norwegian. So it's clustered Norwegian into one. Cluster 5, it seems mostly about tech. Entrepreneur, marketer. Yeah, there is some discrepancies on the last cluster here. It's lots of different stuff. Entrepreneur, freelancer. Marketing, marketer. Seems like it's marketing. So, like, we can go in and analyze how the code has clustered, whatever you found on your timeline. So as the initialization of k-means has a random component, rerunning the code with exactly the same parameters doesn't guarantee to always obtain the same result. I've tested that. The interested reader is encouraged to play with different values for the script parameters. For example, more or less features, just unigrams versus longer n-grams, narrow versus wide range of document frequency, and so on, and observe how these influence the behavior of the algorithm. So at the beginning of our tutorial about k-means, we mentioned how the number of clusters, k, is the main input of this algorithm together with the data. So finding the optimal k for a given dataset is a research problem per se, and it's different from how to perform the actual clustering. And there's a variety of methodologies that one can employ to achieve this purpose. So that's it for this video. And I hope you have enjoyed and learned something from the video, and please do give me a thumbs up for the video, share the video, comment, and subscribe to the channel. Please support me any way you can, and see you in the next video. Thanks for watching.